We need, for this network, just like we do need control and drivers for the QPUs themselves, we also need a full control stack for the quantum network itself. So the control stack will be responsible for generating this entanglement, for distributing it and routing it to the right places at the right times, and meeting the quality of service that the application or the algorithm may demand. Right? So some applications and algorithms may require very fast rates of entanglement between certain processors. Others may require maybe less of a stringent rate, but a much higher fidelity. So we have these knobs we can turn in the quantum network through this control stack to really meet the quality of service that the application may require. So what do we need to actually carry this control stack out? It needs to be able to talk to the rest of the compilers and schedulers to coordinate all of these protocols, from the entanglement network to the quantum computers themselves. So you can see how this is quickly growing in complexity, not just all of the hard engineering that goes on to build a reliable QPU itself, but as you start to consider this data center vision, where you're having interconnections of these QPUs, these subsystems play a really critical role in realizing this vision. So I wanted to touch briefly on the compilers and schedulers for this quantum data center network. So just like with, say, Python code or any other application level classical code, right? We get to write our algorithms and programs at this very high abstraction level. When I write Python, I don't need to know the ins and outs of a transistor. And that's the same kind of analogy that we want to embrace in quantum computing. So similarly, with quantum computing algorithms, we can describe the circuits and the algorithms, the workflow at a very high logical level. Now, we need to start breaking that logical description down through several layers so that those instructions can actually get carried out by the QPUs. And so all of these different QPU platforms speak a very different language at the physical level in terms of the hardcore physics to drive these quantum states in the materials and in the matter that they operate in, but also the instruction sets and the kinds of native operations that they can carry out. So there are many layers in the compilation stack, both for breaking down and decomposing these gates into native operations, but also resource management. Where do I put my qubits, my logical qubits, physically on the chip or across chips? So they're really fun and interesting problems in compilation. Now, this program as well, this logical program and workflow that we can describe, imposes certain constraints, certain rules and logic on the system. So it's not a free-for-all compilation. It has to fall under very stringent constraints. This could be due to the timing and the coherence budgets, the storage times of these physical qubits, the sequencing and the control flow of the algorithm itself, whereby some operations need to happen before or after others. So this really emphasizes not just the role of compilation, but also scheduling, right? And these schedulers that play a role in the data center, they're responsible for managing and scheduling all the instructions, not only for the QPUs themselves, but also the quantum network, right? And so we need to be able to coordinate not just the operations, on a single QPU, but in coordination with the other QPUs that may be playing a role in carrying out this high-level algorithm.